the last topic that we talked about on Wednesday was this principle of work and energy. So now that we have fully defined what work means, it's force times distance, but more specifically, it's the product of displacement times the component of the force in the direction of the displacement. That's the definition of work. Energy is a little bit more abstract. And to visualize, the reason why it's more abstract is there's different forms of energy. There's different ways in which an object can hold energy, can keep energy within itself. The first form that we learn about is kinetic energy, which is the energy stored within the motion of an object. Any object that's moving relative to another object that has mass also must have kinetic energy. So once again, imagine that we have this path S that a particle is moving on, and it's a curved path. It doesn't necessarily need to be straight. It could be straight, but more generally we draw it out with a little bit of a curve. And if it has a curve, we know that it's best to study this object's motion with our normal tangential coordinates. So the tangential coordinate is always tangent to the path and in the direction that the object is moving in. So in this case, the object must be moving left to right. The normal component is perpendicular to the tangential component and is pointing towards the center of curvature. So at that moment, the center of curvature is down and to the right. Now, the reason why this particle is moving, perhaps, is because there's a force that's working on that. Okay? This is some collection of forces. This is a resultant force. Maybe it's just a single force. Who cares? We know that work has to do with only the component of the force that is along the direction of the path. So there's an angle here, theta, that separates the force with the path that the particle is on at this given moment. And if we project this force into the two directions, we would have our tangential component of the force. And if we said F sine theta, that would give us our normal component of the force. We don't care about the normal component of the force when we're talking about work. We only care about the tangential component because, as the definition of work says, it's the product of displacement times the component of the force in the direction of the displacement. So it's only the tangential component that we're concerned about. All right, let's take it a step further. Chapter 13 says that we can invoke Newton's second law, which says that the sum of forces in the tangential direction is equal to the mass times the acceleration in the tangential direction. Okay, well, the acceleration in the tangential direction is equal to v dot, or another way to put that is dv dt. How much is the particle speeding up or slowing down? It simply has to do with the change in the magnitude of the velocity, the change in the speed over time. The tangential component of acceleration only has to do with the component, the speed component, the magnitude component. Well, I can use what I know from Calc 1, that dv dt, another way to write this is just simply dv ds times ds dt. See how those ds's would cancel out with one another, and that would retain dv dt? So there's nothing that's stopping me from doing that. But ds dt itself goes by its own name, which is just speed, the change in position over change in time. ds dt is that value v. Okay, so look what we have here. We have at is equal to dv ds times v. So I can plug that into the equation for the equation of motion up above. So sum of forces in the tangential direction is equal to, these should have arrows over them, is equal to mass times acceleration in the tangential direction. But because we're only concerned with one direction, I can actually get rid of these arrows, can't I? Because it's only a scalar equation at this point once I determine what direction I want to bring this in. So I'm going to get rid of these arrows, because we're only dealing with the scalar equation, because we know the direction that we're considering is the tangential direction. And now I can start plugging in. Sum of forces in the tangential direction is equal to the mass times acceleration in the tangential direction, dv ds times v. I'm going to bring ds over to the other side, and I'm going to integrate fs, it's ft, ds is equal to mv dv. And if I integrate the right-hand side, well, that's pretty easy for me to do. This is from S1 to S2. This is from V1 to V2. The right-hand side of this equation just simply becomes 1/2 mv2 squared minus 1/2 mv1 squared. Now, this collection of properties is called kinetic energy. Kinetic energy, which the book likes to use capital T. Capital T is always equal to 1/2 mv squared. Okay? So you have your final kinetic energy minus your initial kinetic energy is equal to this whole nasty thing. Oh, if only we have seen somewhere recently, that's the integral from S1 to S2 of f ds. Look at that. That's f sub t. That is the force in the direction of the displacement. Well, it turns out we already do have an expression for that. That's called the net work, the work done from 1 to 2. We have now developed the work and energy principle. Work and energy. Woo! Principle. This says that the net work done from state 1 to state 2, I was getting away from me here. The net work done from state 1 to state 2 is equal to the change in kinetic energy, 1/2 mv2 squared minus 1/2 mv1 squared. Now, you may elect to keep it in this form. Personally, I like to rearrange this. It doesn't change the equation at all. But I like to bring that last term over to the left-hand side because I think it shows us something that's a bit more intuitive. This is also the work and energy principle. All I've done is I've brought that last term on the right-hand side over to the left-hand side. And what this says is that my initial kinetic energy plus net work, the total amount of work, is equal to my final kinetic energy. Okay? Kinetic energy is equal to 1/2 mv squared, the mass of the object, 1/2 the mass of the object times the speed of that object squared. Okay? So, if the kinetic energy changes from position 1 to position 2, the only way it could do that is if there was a net amount of work that went into the system. Here's a very simple example. Here's a ball that is sitting on the ground. This ball has mass. The mass of that ball is not going to change. Initially, the speed of that object is 0 because it's sitting on the ground. I want to get the ball over here, and not only do I want it to be over there, I want it to be moving with a speed equal to, I don't know, 2 meters per second. The mass of the ball is still the same. If I want that ball to start moving, you know from experience that you need to kick the ball or hit the ball or apply some force to get it to do that. You need to do work on that ball in order to get it moving. Initially, the kinetic energy of this ball is 0 because the velocity or the speed of the ball is 0. 1/2 m times 0 squared is 0. The final kinetic energy is going to be 1/2 m v2 squared. In this case, v2 is 2 meters per second. So it's not 0. Okay, so I want to speed this ball up. I want to get it going. Well, that means the net work here must be a positive amount of work to get that ball moving. In order to get that ball moving, I need to do a net amount of work. So one way that I could do that is I could take some sort of bat and club the ball with a force over some short distance. When you hit that ball with this baguette, kind of looks like a little roll. When you hit that ball with a bat over a short distance, you're putting in positive net work because there's a force now that's pushing it in the direction that it's moving. That's the only way that we could do something like that, is if we do net work on the object. That's the only way we can get an object moving. Now, you know this from experience, but now we have a mathematical expression that explains this, okay? So the initial kinetic energy plus the net amount of work is equal to 0. Here's another example. Imagine that I have a really poorly drawn car. I'm really good at drawing very poorly drawn cars. This car is moving to the right at, I don't know, 55 miles per hour. At a later time, I want this car to be over here, and I want this car to be stopped. So the velocity at this later time is going to be 0. I'll call this v1, and I'll call this v2. All right. Work and energy principle says T1 plus the net work done from 1 to 2, 1 is over here, 2 is over here, must be equal to T2. Now in this case, T2 is going to be equal to 0 because the speed at the end is 0. T1, on the other hand, 1/2 mv1 squared, the mass of the car is going to be positive. The speed of the car squared is always going to be positive. So that means the net work in this case must be negative if I'm going to have this equal to 0. This will be a positive value. The kinetic energy is always positive or 0. It's never negative. So the kinetic energy is some positive value. The net work must be negative, equals to 0. How does that happen? Well, it's probably because the guy who's driving this car decides to put on the brakes. And as soon as he puts on the brakes, there is going to be a net friction force backwards that causes him to slow down. This is the direction that the car is moving in. This is the direction of the friction force. You can see they are opposite one another. So the work done by that friction force must be negative. Okay? It's that negative friction force that does the negative work necessary to make sure that this balances out to 0 at the end of it. Okay? Takeaway message. What is it about kinetic energy? There's a couple of things we want to always remember about kinetic energy. So the book likes to use capital T for kinetic energy. It is always equal to 1/2 the mass times the velocity squared. Okay? If an object has mass and it's moving with some speed, it must have kinetic energy, which obeys this equation. That's the first thing you want to do. Want to remember. Second thing about kinetic energy. Kinetic energy is ability to do work stored in motion. Go back to this car. This car is moving really fast, and it has a large mass. It could do a lot of work. If you were to drive this car into a picket fence, for instance, it would blast through that picket fence. It would do work on that picket fence, okay? It can do work for you. It could apply a force over a distance for you. So the kinetic energy is the ability of that object to do work stored in its motion. Kinetic energy is always greater than or equal to 0. It is never negative, so never negative. The only time that it's 0 is when the object is not moving. But if the object is moving, then it must have positive kinetic energy. It's always positive because the mass is positive, and the speed, no matter what it is, you square that value, that will be positive as well. Just like work, it has units of joules or pound force feet, or sometimes pound force inches. Interesting. So we said that work is some force times a distance, in a very general way, force times a distance. So 1 joule is equal to 1 Newton meter. Okay. But every Newton is equal to a kilogram meter per second squared. If I rearrange that, that's equal to 1 kilogram meter squared per second squared. This kilogram has units for mass. Meter squared per second squared, that's just velocity squared. So the units do line up with one another because that is our definition for kinetic energy. Now here's the thing that separates work and energy. I said they're very similar to one another, but they are fundamentally different. Work is defined as, in a very general way, force times distance. Now, it's not just any force, okay? It's the component of the force in the direction that it's moving times the distance that it moves in. That is work, okay? But it has to do fundamentally with a process. It says the ball is here, and at a later time it finds itself over there. How does it do that? Does it go this way? Does it go that way? How much work goes into it, okay? Work has to do with how the object gets from point 1 to point 2. Energy, on the other hand, has nothing to do with the process. It is completely independent of the process. Energy can be stored in a number of different ways. We've learned about kinetic energy, which is how an object stores energy within its motion, okay, how it stores the ability to do work. So another way to talk about energy is the ability or capacity to do work. Okay? But it has nothing to do with the process. It's independent of the process. It is actually a property of the object or the system that you're studying. You know how you say that temperature is a property? It's 20 degrees out or something like that. Pressure is a property. Mass is a property. Velocity is a property, so forth. Energy is a property. There's a certain amount of energy that the ball has at state 1, and there's a certain amount of energy that the ball has at state 2. And it's completely independent of the process that it takes to get from 1 to 2. Okay? So it's okay if you don't quite conceptualize what's going on here. It's good to just sort of make a mental note and just say, okay, work and energy are related to one another. You exchange energy to do work. Okay? It's okay if you don't fully understand it. For those of you who are going to take thermodynamics, we look at this in a lot more depth when we study different processes. But work and energy are related to one another, but they're fundamentally different. They have the same units, but energy is a property of a system. Work describes the process. There's a certain amount of energy within your body at this given moment. Okay, you have the ability to do work because you ate your breakfast this morning and you have chemical energy stored within your body that you can convert into work to do something, to walk across the street, for instance. Okay? But you don't say that you have work inside your body. That doesn't make any sense. It's not a property. It doesn't describe the system that you're talking about. Work is something that you do. Energy is something that you have.